Many thanks for the invitation to speak here. My pleasure to be in the seminar. So yeah, so I'm going to present some aspects of regularity of Porous Medium Equations in the precise way which I specify in a second. And right, so this is joined with Jonas Sauer, who's also at the Max Planck, and Eitan Tadmor is in the audience. And yeah, you can find it on arXiv, and it's to appear, the first part of the work. Right, so well, this is what I would like to do today. Let's see how far I get. So I would like to start with some motivation at least. So if you haven't seen the Porous Medium Equation before, at least I have 2 slides to motivate what we are doing. Then I'm going to informally read off what the optimal regularity in terms of Sobolev regularity should be. I'll shortly comment on existing regularity results and then show you some ideas of the proof how to obtain optimal regularity. Right, so yeah, so this will be the equation that we'll be bothered with in the next hour or so. So this is the Porous Medium Equation, which we consider on the full space. Effectively, what we're doing is regularity, so it's more local property, so the boundary data doesn't really matter so much here. And we work in an L1 framework. So the initial condition should be L1. We can also have a forcing, but for simplicity, I just look at this case. And we'll always be considering the degenerate case. So the Porous Medium case corresponds to M in this equation being bigger than 1 when then the equation degenerates. Right, and somehow also for me, the way I started with this work was actually because I wanted to understand something yeah, maybe more complicated, namely this degenerate parabolic Anderson model, which is given with the diffusivity of a Porous Medium equation, but then you have an additional source term, a forcing term, which is quite irregular. So in the parabolic Anderson model, you have this the source term here, which is linear in U, but then this psi is an irregular forcing. It's spatial white noise, so it has limited regularity. And I would like to understand how to make sense of solutions in this case. And yeah, so in 1D, you can still work somehow with the classical theory of para products. But then in 2D, it really becomes complicated. And you should understand in the very first step well how the diffusion actually regularizes the equation. So this is somehow when you look into the theory, Martin Harrah's theory of regularity structures, you first have to understand the heat kernel. So that's easy. And here you would have to understand the improving effects of the Porous Medium operator. Right, so this is how this started. Okay, maybe a second to where this parabolic Anderson model comes from, and this is also one of the derivations of the Porous Medium equation coming from math biology, when you have yeah, some density, some species sitting in space. So you already start in the model here in the continuum limit. U would be the density of some species, and it diffuses due to some microscopic behavior that you observe in the continuous case here. So you have a diffusion operator with some diffusivity constant, coefficient kappa, and some reactive forcing, which is models the reproduction and death rate of the population. And now, okay, so if you have a population which only just randomly move, so your cells just wander around, then you would just get the diffusion as a heat operator. But if you have Croyd avoidance, then this can be modeled by saying that the diffusivity kappa is actually a function of the local density. So if the local density is high, then the cells have more incentive to move in order to avoid crowding and competing for resources. So you would say that then the diffusivity goes up. So in this case, this would lead to a general form where, okay, you have to find what phi should be from the model, but certainly it should be increasing. And you see that this way you end up with the more general type of Porous Medium equation where you have the Laplacian of some nonlinear function. Right, and the particular case of the polynomial then really leads to the Porous Medium equation we had it on the last slide. Now, if you do the same thing, but as in the linear case, now in the situation where you also have favorable or unfavorable surroundings, so this would be a randomly chosen landscape, you would be going to the parabolic Anderson model. And yeah, just an analogy to how this you can be motivated in the linear case. If you say, okay, I look at a species which is diffusing motivated by crowd avoidance, and I have this random potential sitting in the background, then you would end up with this parabolic Anderson case. Right, so of course this is a bit ad hoc because you start directly modeling on the continuum limit, and you would maybe want to understand first the microscopic picture. So say, okay, you start actually with cells and they interact, and then you pass to a hydrodynamic limit and you see the equation popping up. And also this is possible. So there are a number of works in this direction, so just restrict to one here. So you can start with an interacting particle system. You have the agents interacting by the gradient of some interaction potential V, which here we assume to be purely repelling, right? So they should not try to accumulate. Then you would have like Keller-Siegel effects, but they should only like avoid each other. And so you start with the finite particle system, and then you rescale the system by the usual hydrodynamic rescaling. And if you do this, you end up with this equation. So this is after having rescaled in the hydrodynamic way. And you see the structure of the equation that you get in the discrete level is something like a mean field interaction, but this goes jointly with the interaction potential converging to a Dirac. Right? So under the right assumption, under V1, this would converge to a Dirac, so you get localized interactions. And right, if you do it honestly, then so the honest hydrodynamic rescaling, it would correspond actually to beta being equal to 1 in this case. So already saying beta in between 0 and 1, it's a bit of cheating. So this is called the moderate limit, where you still see more interactions of particles. So then the ideas of local equilibria are applicable, and this way you can derive the limiting behavior. Right, so yeah, so what we would like to understand is the behavior of the empirical process when the number of particles goes to infinity here. And because the interaction localizes in the limit, we would expect to have a local equation in the limit. And this is true. And this has been proven, for example, by Oeschläger. So there are a number of results in this direction, as I said. But in this form, it's due to Oeschläger. And he proves that if you assume that at the initial condition you converge to a density, then also the empirical measure it converges to a density. And the density is the solution to the Boussinesq equation, so this particular case of a Porous medium equation. Yeah, so in this form, you can also derive it from some first principle or from a discrete setting. And right, so I said there are many works associated to this. Interestingly, also quite recent contributions by Carrillo and co-authors, which generalizes this work by Lions and Masgalik. Where they actually do like a two-step approach. So they decouple the limit you have here in the mean field and the limit you have in the potential. So you first go to the mean field limit, you get a non-local diffusive equation, then you localize the interaction. And this is it's another way which sort of corresponds to beta being very slow or very small to derive the equation, and yeah, has been done in these papers. Yeah.
Our motivation was quite different.
Yeah, it was numerical, right?
Numerical.
Yes, of course.
A smooth particle hydrodynamics, and to look at Porous medium equations and
right.
transport equations.
Exactly.
Which you can use particle methods.
Exactly. So this was numerical, but yeah, so you prove in the end the same thing that we would have to do. Right. Okay, and then now you could set this into a random framework. You have a branching particle, so you should have depth and multiplication of particles, and then you would end up again with the degenerate parabolic Anderson model. Okay, so yeah, this is the two slides for the motivation of the equation that I wanted to give, and now let's have a look at the regularity of solutions in this case, and to give you a very firm first idea, if you haven't seen it before, then to get an idea that something interesting should happen when the solution or the value of the solution hits 0, you can informally do the following computation, that you take the Porous medium operator. So I write this bracket always for the monotone power, and then you just expand formally the derivatives. So you pull in the gradient, and then you pull on the divergence, and you see what comes out. Okay, up to, so highest order term would be a diffusive term, but the coercivity coefficient, it sees the value of the solution. So when U goes to 0, the diffusivity goes to 0. which could, I mean, just looking at this, you could expect that somehow the rate at which the support of a solution expands, it could be finite, because the rate of diffusion goes to 0 when the solution goes to 0. And you could expect that the regularity is limited at this interface where u hits 0, because then the Laplacian goes to 0. Okay, of course, this is very informal to do it this way. You cannot justify doing this because things are not regular enough. But when you look at explicit solutions like the Barenblatt solution, then you see that indeed this happens. So the Barenblatt solution is somehow the analogon to the Gauss kernel in the heat equation, so in the linear case, because it starts at the Dirac mass and then solves the equation, and it's a self-similar solution. Okay, so self-similarity is it's written here, so you have just one profile, and it's just rescaled in time. And okay, I write the explicit profile here. So, well, the point here is that okay, this is the initial condition. Well, the initial condition is the Dirac. This is after some time has passed. And the point is that you see the support only expand at a finite rate, which is, of course, in difference to the linear case. And you also see that you have kinks in the solution when this value hits 0. So the derivative has jumps. Yeah, you're not better than C1, which you can see from this picture. Okay, so yeah, this is like the hand-wavy case to look at regularity, and you see that things happen, but we want to understand it more precisely. So what should actually be the optimal regularity that we should expect? And then, well, you can make a formal argument by rescaling. So this is what I do here. So let's pretend that we managed to prove a quantified regularity estimate as you would have it in the linear case, in the sense that we can prove, we pretend we can prove that for any initial datum in L1, you get to some fractional regularity in space. So you get the homogeneous Sobolev space here, W dot of differentiability order S and integrability P. And you have this for any solution. Okay, so if you were to manage to prove something like this, then you can derive necessarily conditions on the exponents P and S from this, just by rescaling. So pretend you have this, you rescale the solution in the self-similar way, so that the rescaled solution, it again satisfies the equation. So it's a solution again, so the inequality has to hold, and you plug it in, and you see how the inequality behaves with respect to the rescaling parameter eta. Right, so yeah, so the logic here is if you assume U is a solution, then this is the right rescaling so that U twiddle is a solution again. So it has to satisfy the energy inequality. You plug it in, you get eta appearing in this equation depending on the parameters you put, P and S, and then you can derive counter examples or contradictions if they don't match.
I have no problem
Yes.
with the scaling in space. So the scaling in time is going to modify the entropy of
Yes,
the
so
problem. So do you want to make an assumption on how the constant depends on time in the lemma? Or
no, so but you scale in the right way so that it only blows up so it only makes the estimate better. Right, so you cannot choose eta to infinity.
You're reducing, you're not using all etas, you're using...
Yes, so you then only allowed, I don't know which one, to take eta down to 0 or to infinity so that it goes, yes,
Okay.
yes. Right, so we only use this one, and then you see that automatically you get these restrictions that something like this can only hold up to integrability order m and up to differentiability order 2 over m. Okay, and yeah, the sanity check always should be compared to the linear case, and there's of course the right thing up to an epsilon, right? So this would be maximum regularity, where you would get p equal to 1 and s equal to 2. Formally, you can prove 2 minus epsilon, but this estimate somehow suggests the optimal value. Okay, of course, this is no proof that this is the optimal regularity. It's just an indication, because it could still be that you can prove that solutions are regular, but you don't have this quantified way. This is no counter argument for this. But this already suggests that actually, because we only use rescaling, these estimates that we derive here should be saturated by the self-similar solution. So this suggests to look at Barenblatt solutions and to read off what you can prove there. So let's write down the Barenblatt solution again. And then we can see that U takes values in the space where you have LM integrability in time and LM integrability in space for the differentiability order S only if S is less than 2 over M. Okay, so this is in accordance with the formal estimates we derive up here. So this really tells you that there's the optimal value of the integrability and differentiability index would be M order of integrability and 2 over M order of differentiability. There's nothing more you can hope for. Right, and I mean the proof of this, it's again very simple. It's just using that it's actually the self-similar solution. Right, so yeah, so what is known, maybe, yeah, I've just prepared one slide, which is a bit dangerous because it's a super well-studied topic, and there are many, many, many works. So the slide has to be somehow missing a lot of contributions. So I don't want to go through them in detail to avoid missing out on results. Just to make some points here. So historically, I think one of the first ways how regularity was looked at in this case was in terms of continuity. So there are a number of works in proving continuity of solutions, and then also Hölder continuity, so in a quantified way. And if you follow through the proofs, so they rely on de-Giorgi-Nash-Moser iteration arguments, and this way you get some form of regularity. So as Hölder regularity, as you also would in the linear case, but typically it's not very good. So in the linear case, you would then bootstrap with Schauder estimates, which you cannot do here. But you can go into the proofs and read off what kind of Hölder exponent you actually get. And what is proven, if you follow this would be a Hölder regularity of order 1 over M, which is a Hölder exponent which always lies in between 0 and 1. So in particular, you cannot see from this that in any case, even if M is close to 1, that you get more than 1 order of differentiability. Right, and then there are many different ways on how to look at regularity. So maybe this is important to say that the way I want to analyze regularity is in terms of this kind of genuine regularity result, which doesn't suppose additional restriction on the initial condition. So if you say, okay, I start with an initial condition, which is somehow well prepared or close to the self-similar solution, there's more you can say. But here we really just want to say, okay, my initial condition is in some LP space, for example, and then have a generic statement about the regularity. So, yeah, and then in this case, we are in particular concentrating now on regularity in Sobolev spaces. So the way I already had it on the last slide, this is the way I would like to understand regularity. And if you ask in this direction, then actually there's not so much known. So there's, right, to my knowledge, this is addressed in this work by Lions, Pertin, and Tatmo in 1994, where they introduced the kinetic formulation for conservation laws, but they also comment on the second order case. And at least it's already realized that using this, you can show compactness, which is a mild form of regularity and maybe also already quantified. Then there's a work by Abmeyer, which is, I would say relatively simple in the sense that it's just using energy estimates to deduce regularity. And maybe here the most important work that I'm referring to in the spirit of what we're doing is by Eitan Tatmo and Tao in 2007, where they prove regularity in Sobolev spaces. So let's see so now I'm going to comment a bit more in detail on what is shown here, so what is known in the literature. So, so we introduced the homogeneous Nikolsky spaces, which is it's just a particular case of a homogeneous Bischoff space. So this Nikolsky space SP is just the homogeneous Bischoff space of differentiability order S, integrability P, and third index infinity. And and then going to either of these works, they set up an L2 framework to understand regularity of the Porous Medium Equation, and they prove that you get regularity in the sense of having Lm plus 1 integrability in space-time, and an order of differentiability of order 2 over m plus 1. Okay, so you see that this is already different from the scaling we read off on the first slide, because that was m integrability and 2 over m differentiability. And what you can notice is that because m is bigger equal 1, the order of differentiability you can see from these results always is bounded by 1. So again, similar to the case of Hölder regularity, you cannot cross this borderline of one order of differentiability. And of course, this is, this is inconsistent with the linear case, right? Where at least when you start in L1, you would expect that you should gain almost 2 derivatives, right? So yeah, we'd like to understand why there's this inconsistency in terms of optimal or highest order of differentiability that can be shown. Okay, now if you recall the linear case, you could shout, well, actually, this doesn't make sense, because if you look at the heat equation in L2, then also you should not expect that it's going to be in W22, because you would have to start with them in the right trace space already in the initial condition. So you would have to start not just with L2, but with L2 and some regularity. But actually, here we can, okay, this would just lead to saying that you shouldn't work in L2, but in L1 to see the optimal order of differentiability. And to some extent, this works. This is somehow a soft argument, which you can write down. So yeah, just again, looking at the Porous Medium Equation with L1 data now, it's just energy estimates that I'm writing down here, but putting them in like almost L1 instead of L2. You can see that if you restrict to the case where m is bigger than 2, the initial condition is basically L1 plus an epsilon. The forcing is L1 plus epsilon. Then you get regularity in almost the scaling that you would like to see. So it's almost Lm and almost 2 over m here. Right, so this seems like L1 is the better space to look at. But you see this doesn't actually solve our problem to see more than one derivative. Right, because this proof, and this is really intrinsic to the proof, because where you write down an energy estimate, meaning that you take your diffusive operator, you integrate once by parts, then you get a bound on somehow the first derivative of some function of your solution. So from something like this, you cannot hope to get more differentiability than one order, right? Because you just control a gradient at the first site. So really, with these arguments, you cannot hope to see anything bigger than 1 here. And yeah, I mean, on technical level, this is produced by this working out only for m being bigger than 2. So again, actually, the regularity that we can prove is of an order less than 1. Right, so yeah, this still leaves the problem of seeing more than one derivative when m is in between 1 and 2. Right, and this is the starting point of what I wanted to present here. So the starting point of asking about how to prove optimal regularity in this setting. Right, so I'll start with actually writing down what we show. So again, Porous Medium Equation in a 1 setting. And then we prove that if you start a little bit better, so you have to work in L1 plus epsilon. So the initial condition is L1 and L1 plus epsilon. You look at the unique entropy solution. So I'm not speaking about Weil-Postness. Let's just accept that there is a unique solution. Then for any differentiability index S being less than 2 over m, and then any integrability index P being less than m, we prove that the solution actually takes values in LP in time, W as P dot in a space. Okay, and then you see that both looking at the Barenblatt solution and both looking at the scaling, this is the optimal result you can hope for, right? Up to an epsilon, right? So up to an epsilon in several ways. I'll comment on that later. But yeah, up to this, really it works, and there's no restriction on m, right? M is bigger than 1, but it can be close to 1. So this tells you that you actually get differentiability index up to order 2. So this is a consistent estimate to the linear case. Right, and you can quantify it, so you also get a quantified estimate on this. Okay, so yeah, so what I would like to do is not to go to the proof now and step by step somehow, because this would be too long, but I would like to explain some of the ideas that we needed to have in order to come up to this higher order of differentiability. And yeah, in order to do this, I present a proof in quotation marks, because actually we see that this is not going to give the right proof, but it will give the right ideas to understand what we have to do. So yeah, so everything I'm doing now relies on the kinetic formulation. So I already hit hinted on this on the I don't know, 4th slide. And yeah, it corresponds, so it's, I think originally was motivated from conservation laws. This goes back to, in this language, it goes back to the work by Lios Patam-Tadma we already saw before. There's also early contributions by Jan Brenier in this direction. Just, yeah, saying that it's a kinetic formulation. I guess it's the first time in this paper, or yeah, around that time at least. And then this was generalized to parabolic, hyperbolic equations in this work by Chen and Pertam. Right, so what does it mean? So the kinetic formulation means that instead of looking at the solution U that we want to understand, we actually look at the kinetic function associated to the solution U, which is given by this kind of indicator function. So chi is given as the indicator function basically of U taking values in between 0 and V. V taking values in between 0 and U, this way. Right, so looks a bit strange. So one way to think about chi certainly is that it gives you a way of parametrizing entropies. So you could think of this new free variable V, the velocity variable, as parametrizing a whole set of entropies, right? And the entropies being these nonlinear functions. This is one way to interpret it. It's called kinetic formulation because now you see you introduce this new free variable, so your solution now depends on T, X, and velocity. And in an analogy to Boltzmann equation, this could be interpreted as a kinetic framework. So the benefit, or the interesting realization now is that if you make this maybe odd-looking transformation to your solution, then you still get a closed equation again for chi. So you write down now what chi satisfies as an equation, and you see that you get to this guy. Right, so this is what happens to the Porous medium operator, and the interesting effect here is that this becomes linear in chi. Okay, so you start with a nonlinear equation, you make this nonlinear transformation, and the resulting equation becomes linear. Of course, you can, I mean, this would be cheating. It's not actually linear in terms of U because you have this nonlinear function, and you also have this entropy dissipation measure Q. So the meaning of this term is that you have the velocity derivative of some non-negative measure. And this non-negativity of the measure corresponds to entropy being dissipated only in a positive way. Okay, so this means that you're looking at entropy solutions. Right, so yeah, and what you can say, and what has been pointed out in these previous works, is that actually looking at kinetic solutions, so you'd call U a kinetic solution if the associated kinetic function satisfies this equation for some non-negative measure Q. This is equivalent to saying that you're looking at entropy solutions, renormalized entropy solutions, actually. Right, so you could say, well, it's just in an equivalent way, so what do I gain? The point is that this equation is better suited in order to understand regularity because you have some linearity in the equation now. Okay, and this we want to exploit. Yeah, so this is the one reason, but there's another somehow benefit of writing down the kinetic form because it also gives you a good way to decompose your solution. So on this formal level, we saw that somehow the difficulties in the regularity of the solution should come from the values being small. So this suggests that it should be a good way to decompose your solution into a part which only sees small values and a part which only sees large values. Maybe not so immediate how to write it down, but once you have written down the kinetic function, actually it is immediate. So I write it here. So you can write U as just the velocity integral of chi, where this is just a calculus fact because this is something like an indicator function. If you integrate it up, you get back your value. But this gives you an immediate way because now, well, in the integral, things are linear, so you can just split up this integral into small velocities. Right, there's U1, which you would think of as being something which doesn't have much regularity, and part of large velocities. Right, there's U2, where you would think that the solution, or U2 should actually benefit from the equation because that's non-degenerate. Right, so this is the composition of U, and now for U2, okay, because here velocity is large, you would think that the degeneracy is actually not seen. So on this term, you want to use the equation to read off regularity. And the way to do it is just, okay, once you have written down this is a linear operator, you can do variation of constants, so you get the mild formulation of the equation, like this. And, but if you integrate this up, in lambda being bigger, v being bigger than lambda, you get the representation of u2 by using that it satisfies the equation. Okay, and somehow this, yeah, you can see that for u2, actually, you would expect that there's some regularity because you have the heat operator, okay, rescaled in v, but effectively the heat operator acting on the data. Okay, so yeah, so the takeaway message from this slide, I guess, is that we have found a decomposition of u into two parts, one which is irregular, one is regular, and we have a scaling parameter sitting in between these two guys. So this shouts real interpolation. Okay, so if you manage to bound both parts, then you can just use real interpolation to deduce the regularity of u. Okay, so how to do it? So the first part I said, well, there the equation degenerates. So we actually don't want to use the equation. You just want to do a trivial estimate. Okay, and we can do this. So u2 in the LR norm, this is just plugging in the definition. u2 was just integrating out the kinetic function for small values of the velocity. And you see this scales like lambda. So when lambda goes small, the contribution is small. More interestingly is to estimate the regularity of u2. I'm just recalling here how it was defined. And here we can just use heat kernel estimates. Okay, so of course you have to be a bit careful because this term is more complicated. So here you have to integrate by parts once. You take the derivative of the semi-group. You can see that somehow terms or powers in v pop up and so on. So there are a number of lines of computations in between. But effectively you use how the heat operator acts in L1. And thereby you see that the second part, u2, gains regularity in the sense that it's L1 in time and w2 alpha 1 in space, where alpha is anything less than 1. Right, and of course it's important to keep track of how this scales in lambda, right? So here we have a regular part which blows up in lambda when lambda goes small. So this is precisely what you would like to see in order to do real interpolation, and now you can close the argument. So you just estimate the k functional by this decomposition, and you can read off what you would get as regularity. But of course, the question now would be if this actually does the trick, right? So we wanted to see something of derivative order higher than 1. So the sanity check would be, again, let's just plug in the linear case. So if you do this, then in the linear case, well, this just drops out. So you have scaling lambda to the -1 here and scaling lambda here. So when you do the real interpolation, you will see the sort of the regularity in between. So what you see is actually that by this argument, you would get that u is in L1, W11. Okay, this is not good, right? So this is still just one derivative, and it's not a very good estimate you end up with. So yeah, and at this point, one should stop, and maybe also this is interesting to see in comparison to the case of hyperbolic conservation laws, because there you have a similar difficulty. So for example, if you look at Burger's equation and you want to prove regularity of the solution just by kinetic theory, then what you would get by kinetic arguments is that the solution is 1/3 Sobolev differentiable in space-time. And this is, of course, not optimal, right? Because in Burger's, you know that the solution actually is BV. And the problem for both of the methods, here and in conservation laws, is that we don't understand how to use that we're looking at entropy solutions. So the only thing we use here for the kinetic measure is that it has finite mass, right? And we don't understand how to use that it has a sign. And somehow this we should be able to do. And this explains precisely why we can't get optimal regularity just from this result. Right, so what can we do? And there's one idea here that actually we know a bit more about the kinetic measure. Namely, we can prove, and I'll show this on the next slide, that actually Q has singular moments. So it doesn't only have finite mass, but you can integrate singular moments in the velocity component against the kinetic measure. And this immediately helps, because you see we are concerned with the power of the lambda we get here. But well, knowing this, we can just introduce in this term. Once we have integrated by parts, we can just multiply a v to the minus gamma on this term. We gain a v to the gamma here. We estimate it by lambda. So the scaling in lambda just changes by a power plus gamma. right? So this term and this term was just multiplying a 1. So the scaling becomes better, and actually much better. So gamma can be close to 1. So yeah, I guess in the linear case it would mean that m, so linear case m equal 1, this would be 0. Gamma is close to 1, so effectively this is almost 0. So you don't see any blow up anymore in this scaling parameter. So actually in the linear case it would immediately go to the optimal regularity. And this is also true here. So let's say we work with integrability order 1 for this first term. I'll explain in a second why we do this. We choose alpha as large as we can, so up to an epsilon, we choose equal to 1. Then what we obtain, just from real interpolation and this decomposition based on the velocity component, is that the solution takes values in this real interpolation space, which embeds into L1 in time, W2 over M in space. Okay, and this is the right order of differentiability that we want to see. So here, in terms of differentiability order, this already gives the optimal estimate. Right, and what we had to realize is to use these kind of singular moments of the kinetic measure. It's not fully what we want. I'll get to that in a second, because the integrability order is not optimal, right? This is only L1, but we want to see Lm in space-time to get optimal estimates. But yeah, maybe because I'm saying that having these kind of singular moments finite is essential to what we're doing here, we should check that this is actually the case. So it's an easy computation. So you go to the kinetic formulation and you sort of do energy estimates on this level, meaning that you take your kinetic form, you multiply against some power in velocity. Yeah, so I just multiply it against v to the power 1 minus gamma and integrate in space and velocity. Then you realize that this is of a divergence form, so it just drops out. It's 0. And the kinetic part, okay, you integrate once by parts, which gives you a good sign, and you see precisely the singular moment popping up. So what does it mean in terms of integrability that we're working with? Right, you have to understand what this is, but this is again an explicit computation, so chi is still the indicator function of v being in between 0 and u. So if you take the integral here, you just get the antiderivative of whatever you applied it to here. So antiderivative of this guy is 2 minus gamma divided by 2 minus gamma. So you see the L2 minus gamma norm popping up. And now we wanted to choose, to get optimal estimates, we wanted to choose that singularity as high as possible, so gamma close to 1, telling you that actually this corresponds to working basically in almost L1 spaces. But it also explains why we're not actually reaching L1 here. Right, so in the end we get this estimate, so you can choose any gamma in between minus infinity and 1, and you get an energy estimate, and the point is that this guy is finite. When you make this rigorous, you have to approximate, okay, and then you prove this on an approximative level, and you want to pass to the limit. The way to pass to the limit in this a priori estimate, you use Fatou's lemma. And at that point, in a sense, you also use, indirectly at least, the non-negativity of the measure q, right? Because only then Fatou's lemma would apply. So in the estimates, we use the singularity of the moments, but in order to prove that this singular moment is finite, you also use that q has a sign. So indirectly, at least, this comes in. Right, so this works. So yeah, so what did we obtain so far? Let's go back to the estimate I had already on the last slide. So far we had that u takes values in this real interpolation space, which gives the estimate we want in terms of differentiability, but not in terms of integrability. So, and what we used for this was just these two estimates. And okay, now you can say, okay, but obviously I didn't argue in an optimal way because I just chose r equal to 1. So I threw away that we actually know that this guy is much more regular than just L1. You can do this in all LR spaces, so it should be almost, you should use this with r being close to infinity, actually. But there's a technical point here which is problematic and which doesn't allow to use the proof as I presented it. So this is why proof was in quotation marks, because when we look at the real interpolation we get when we actually use r being big, then we're trying to interpolate these two spaces. Right, so yeah, this guy coming from here and this guy coming from here. But then the problem is that neither of these spaces embeds into the other one. Of course, you can still write down what real interpolation is, but the problem is that if they don't embed, then you actually have to bound the k function on the full real line, whereas if you have one embeds into the other, you have only to bound the k functional for small values. Right, and this is essentially used in the proof. So yeah, just with this, we don't know how to do it. And yeah, and this motivates now to actually deviate from the proof that I've shown you, which was just based on real analytic methods, and to go to Fourier space in order to modify the decomposition of the function that we saw. And it turns out that actually it's not the right idea just to decompose concerning the value of the velocity. And this becomes very natural when we pass to Fourier space. So let's see how this goes. So yeah, so we're going to use a microlocal decomposition of the kinetic function or of the function u. And what we aim to get is that to write down a new decomposition where all the regularity is moved onto the first part. So this was the part where the solution degenerates, where we had high integrability, but we had no differentiability. But now by modifying our decomposition, I claim, and we'll see how it works, we can actually also move the regularity on the first part. And then real interpolation is fine, right? Because now this is locally a small space, so this embeds locally into this L1 space, so we can close the real interpolation argument. And then using that actually we can do this for integrability order very large, we get to optimal integrability, and we get the up to an epsilon optimal estimate that we want to see. Right, so yeah, and now I would like to motivate the microlocal decomposition because it sort of naturally comes up. So again, we start with the kinetic form, but now we go to Fourier space. So we space-time transform, take space-time Fourier modes. Of course, yeah, okay, you have to extend it to full space and so on. So there are some technicalities that I leave out. Effectively, in the end, you go to this Fourier modes in space and time, which tells that the time derivative, of course, becomes this guy, and the diffusion operator becomes this scaled diffusion operator. And okay, I introduced this name, script L, being the linear part of the kinetic formulation in Fourier space. Okay, and then, well, so what does it mean? It just means that the kinetic formulation is this Fourier multiplier applied to chi hat equals to the right-hand side. So formally, you can write chi hat as being 1 over L times the right-hand side. And now, yeah, I mean, it's very simple. So as in the linear case, you would say that, well, whenever this Fourier operator becomes large, you would gain regularity. But when this guy becomes small, you don't gain anything. So what you should actually penalize is not just the velocity component, but this full guy. So you should decompose according to whether L is small or L is big. Right? And in this Fourier picture, it's quite clear, because once you know that L is big, you would gain something from this guy. Yeah, but this is a microlocal decomposition in the sense that now you penalize not only, or you don't fix only the Fourier mode, like you would in Paley-Littlewood decompositions, but you fix or penalize the product of these two guys. Right, so yeah, let's write this down rigorously. So we start with the decomposition of the one, as usual, in this dyadic way. So we have like a cutoff function of a ball, and then phi 1 would live on an annulus. And this is the usual decomposition of Fourier space. And then you can write down this microlocal decomposition of the solution. So chi hat is just given as the case where things degenerate. So phi naught is cutting out the ball. So this means that on this set, L divided by delta is bounded. Delta is now our interpolation constant. It used to be lambda before, so now it's delta. And this part, here you, again, the same spirit as before, you wouldn't expect to use the equation to read off the regularity because that's degenerate. And in contrast to this guy, where the action of L is localized onto this dyadic level 2 to the power j times delta. So in the second part, you would want to use the equation. Right, so this is the microlocal decomposition, and then we also use a Paley-Littlewood decomposition to be able to work on fixed blocks, right? But this is more standard, so I'm not going to actually comment on that part. Okay, so I said this, and right, so now what we have to manage is to establish good estimates on this function chi naught. So on the degenerate part, because then the idea or the aim we had in mind is to prove that actually chi naught is very regular. So it has good integrability and differentiability. So on that line we have to work. And there are some difficulties actually to prove this, right? Although we're not using the equation for this guy, it's not direct how to do. And yeah, so there are these kind of difficulties. So if you go back to averaging techniques, say for hyperbolic conservation laws, typically where they work very well is in L2. So in L2 you get rather easy good estimates because you can use Plancherel equality. So you throw away the Fourier transformation ones, and then you can get good estimates. And in order to pass to general IP spaces, you typically interpolate with worse estimates, say in L1. So you have a trivial estimate in L1, which doesn't actually give you regularity. You have a good estimate in L2. Then you interpolate these guys in order to get to general IP spaces. But this tells you that when your integrability order goes away from 2, the estimates become very bad. And we would like to understand the regularity in LP spaces for p being close to infinity. Okay, so yeah, this part you have to deal with somehow. And this we do by using actually the isotropic nature of the equation. So there we go back or go away a bit from averaging techniques and use isotropy. Then, okay, I made the point about the singular moments. We have to use this. And then there's another technical point, which is that when you derive regularity estimates, like, for example, for conservation laws, the way you get to good regularity estimates is by bootstrapping. So you prove a first estimate that tells you that actually your solution has some fractional regularity. Then you say, okay, if this is true for my solution, then also my kinetic function has some a priori regularity, and then you plug this into your proof and you bootstrap. Okay, and this works, and it's a nice and effective method for hyperbolic conservation laws, but you see that this is intrinsically restricted again to having order of differentiabilities less than 1. Right, because even if you manage to show that this guy is regular to some higher index somehow, then at this point it fails, right? Because this is an indicator function and you can only take the derivative once. So this way you couldn't bootstrap. So yeah, you have to come up with a different way of completely avoiding bootstrapping arguments. Right, so I guess, yeah, I would explain a few things about how to deal with this point and this point. Because this one we saw informally already in the real analytic proof. Right, so yeah, we introduced this notion of isotropic truncation property, which is, well, the name is chosen after the idea of Aidan Tutmore and Ernst Tau to introduce this uniform truncation property. And we call a function m, which should be our Fourier multiplier, taking a Fourier mode and the velocity component to satisfy the isotropic truncation property if for every bump function, psi naught, depending or being supported on a ball, and bump function psi 1 being supported on an annulus, the corresponding multiplier defined by penalizing m to be small. So this is precisely what we had in the equation. We cut off in microlocally the small components where L degenerates, and we localize on some Fourier level. Then we assume that taking the LP multiplier norm of this Fourier multiplier, we can control how this guy behaves in the velocity component. In the sense that the LP multiplier norm is still integrable in the velocity component and is bounded by the set of degenerate velocities. Right? So this is, again, reminiscent of what you would see in conservation laws. You always see these kind of sets of velocities where your operator behaves not nice.
What do you mean by isotropic?
Well, because it's, because it's radial. So
it's radial in psi?
Yes, radial. So maybe that's a better word. Yes, because otherwise it doesn't really make sense to speak about this guy, because this only depends on the Fourier mode and not the direction. So, yeah. Right, so yeah, it would be useless, of course, if you couldn't check it. So the point is that when you look at Fourier multipliers of the form that we have in mind, which is, yeah, in the Porous medium case, it would be b being the power and velocity, then actually you can show that these kind of examples satisfy the isotropic truncation property. Okay, you have to work a bit, but effectively, okay, you apply Hermander-Michelin multiplier theorem, you trace the constants in what you do, and you see that indeed it gives you these kind of bounds. So now let's see how this is useful in order to pass through general LP spaces and to avoid bootstrapping. And this is all concerning actually the degenerate part of the equation. Right, so we have to put an assumption to quantify the nonlinearity of our equation. Again, this also you know from conservation laws, in the sense that we say that the mass of the set of degeneracy, it should decay in the Fourier mode and in delta. Okay, this is okay. Now here I put it as an assumption, but if you plug in just the explicit case which we are looking at, where m is just being given by j squared times v to the power m minus 1, this is just an explicit calculation. Then you get this bound immediately with beta equal 2. This is the order of the equation, and alpha being equal 1 over m minus 1. Okay, so this is easy to check. So let's see how to estimate the regularity of the degenerate part of our solution. So we have to estimate the LP norm of the J Paley-Littlewood block of chi naught, so of the degenerate part of our microlocal decomposition. Okay, I'm writing down just the definition of chi naught, right? So we had microlocalized the action of L, and we have fixed the spatial Fourier mode onto level J. So then what we do is we pull in the LP norm. Of course, this is a dangerous step, right? If you were to think about hyperbolic equations, this is not something you should do. But in the isotropic case, it works. So then you will just left with estimating the LP norm of some Fourier multiplier. Okay, so I'll just write down the definition of the Fourier multiplier norm. And then you apply, from here to here, you apply Hölder in the velocity direction. Which is, I mean, this is a super harmless step, but this is an important step. Because when you go back to the standard ways of doing averaging lambda for conservation laws, it is at this step where you can realize how to avoid bootstrapping arguments. And I think the first paper where I've seen how to do this was by Jabin and Pertam, where they realized that you should, so in conservation laws, you should exploit that the kinetic function always has one derivative in the velocity component. And actually, where you use this is just the same thing. They use it at this step, because here they argue that you should put the derivative in v here and an antiderivative in v here, which improves the estimates and allows you to avoid bootstrapping. And yeah, so you see here it's we do something similar, but it's just a Hölder inequality. We don't have to distribute derivatives. Right, so we get to this part, but then by the isotropic truncation property, this guy is actually bounded by the mass of the degeneracy set, which is bounded by this, so you end up with this estimate. Okay, so I guess these lines are maybe hard to follow if you're not like used to these kind of averaging techniques, but if you're not, then you just read from this line to this line to grasp what we have gained. Because what you can see now is that we have estimated the jth Paley-Littlewood block of the averaged localized part of our solution in terms of a decay in a capital J, right? So this decay gives you regularity. So you can just multiply by it and you get Bischoff space regularity. And you also see the behavior in delta. So the scaling parameter for our real interpolation argument with a positive exponent as you would expect. Right, and the point is, of course, that this computation we can do for any LP. So this doesn't matter here. And this is in contrast to just being able to work in L2 when you do averaging in conservation laws. And we exploit essentially here that with the radial nature of the equation. Right, so somehow, instead of using that chi as a derivative and velocity component, we use that the a priori we know that's in L1 and L infinity here, because then the right-hand side here is finite. Right, and now I'm dropping the full treatment of the second guy because it just takes too long. So there you have to use averaging techniques in their original form. But yeah, I'm saying that if you piece everything together in the end, by being able to treat general LP here, you are able to go to the optimal regularity and order of integrability. Okay. Right, so this is the main proof. So maybe I should, okay, I don't have so much time, so maybe I just comment on a few things now. So I initially motivated these questions by asking actually something about stochastic PDEs, like the degenerate parabolic Anderson model. And we can indeed apply all what I've shown you also to this more irregular situation, right? So there the problem is that this guy is not regular. It's just like a C minus 1/2 distribution. But we can see, like using paraproducts, how to make sense of this product. And then you can read off the regularity. And again, it leads to optimal regularity in this worst setting, right? So you lose some regularity of the solution by being in the forcing being bad. But this is, again, the optimal one to expect and consistent with the linear case. Right, so in this sense, in the way we asked about optimal regularity, we are somewhat satisfied because up to an epsilon we can actually prove it. But if you think about it a bit more, then there were certain points at which we're actually not quite optimal yet. So yeah, so what was left open is, first of all, I only talked about, yes?
On the Anderson models, this is a 1D so.
Yeah, this is a 1D, yes, very important.
And,
yes.
What are the assumptions? M is greater than 1, right?
M is, yes, in between 1 and 2 in this case. I didn't write it.
You mentioned it
yes.
Initially, not here.
Yes.
Not anymore.
Yes, so it's in between 1 and 2.
Yeah, okay.
Otherwise, I think the regularity gets too bad, right? I mean, it depends on M, so. Yes, and you want to be able to define this product in a classical way. So you don't want to renormalize yet. So yeah, you need at least.
One is excluded. In the linear case,
yeah, but it's known, so it's different. Yes. Right, and 2D would be already super critical in a sense, because then this product would not, I mean, definitely the product wouldn't make sense classically anymore, because the solution would be just expected to have one derivative. The spatial white noise in dimension 2 is minus one derivative, so the product is just not defined anymore.
I wonder if something like the higher type scaling limits while smoothing the spatial white noise might not be a problem to look at. Because that's, what they did recently with research in Porous is Laplacian U plus a function of U
right,
times
yes.
The smooth white noise
yes.
in order to understand what the limits are. But of course you have to do some scaling analysis, and clearly here there might be another scaling analysis, which might make some sense of the spatial white noise, because writing directly a continuous model with a spatial white noise might be too late already. I mean, we have missed.
Ah, you mean, yes, okay, I understand.
So in some sense going backwards a little bit might help to understand what are the real, the real things that go bad and
yes.
we can extract. I don't know. I mean,
no, I agree that we would like to do this. So far it's quite unclear how to actually do it, because when you look at the higher theory, you always use that you have the linear equation to compare with. Like you expand your solution in terms of the linear equation. And here, okay, you.
it's a more recent work.
Okay, I see. Right. So, but yeah. So here we are in 1D. So in that case, we are free of these difficulties. Yes. yeah, so some closing remarks, just so I won't get to how to do this, but so far we only treated space regularity, which is somehow an unnatural restriction, so we should understand regularity really in space-time Sobolev spaces. We didn't really treat L1 initial data, but L1 plus epsilon, which seems like a technical point, but it's sort of relevant because then actually this avoids or prevents us to actually applying it to the Barenblatt solution. So it hints at optimality, but it's not exactly clear. So the Barenblatt solution, it starts at the Dirac data. So it's a measure, but if you have estimates in L1, this would apply to measure initial data. So you actually want to treat L1. And also, we didn't do any higher order integrability. So if your initial data is already in a row, for some row bigger than 1, you would expect that your solution should have better integrability estimate, maybe with a worse differentiability index, but you should gain integrability. And also, this doesn't follow from what I've found so far. And yes, so I guess the task here is to give a very, to do the full thing. And yes, this is the second work I mentioned in the beginning. So jointly with Jonas Sauer and Aiden Tatmore, I display here the result. Maybe take some time to digest. So this includes somehow all the limiting cases that you would actually want to understand. So it does give you space-time regularity. So you get regularity in the direction of time and in the direction of space in an optimal way. So you can redo again these scaling arguments to see what the optimal regularity in these directions is, and this is precisely these guys. It does give us L1, a full L1 treatment, because this row can be 1. So there's no restriction on L1 plus epsilon, so it immediately applies to the Barenblatt solution. It gives you how time and space regularity scale. So here, again, you can make the sanity check to the linear case, which would be the classical linear scaling in time, quadratic scaling, twice the scaling in space, which is modified if you look at the nonlinear situation in this precise way. It's also the right scaling. So yeah, so with this, you get a very complete picture and like a definite answer to optimal regularity without somehow unnatural restrictions on having a little bit better integrability and so on. And actually to prove this is quite a bit of work. So it's not that direct because, well, I guess the first point is that actually the functional setting is not that clear. So you work in anisotropic Sobolev spaces here, but the arguments are well adapted to homogeneous Bezoff spaces on the technical level. So we should work with anisotropic homogeneous Bezoff spaces, and you have to find the right way how to actually define these guys. And this is, this leads to somewhat non-standard spaces, like these Schmeisser and Treibels dominating mixed anisotropic homogeneous Bezoff spaces. Right. So I was very happy when I saw that somehow it's natural to apply them. So it's, to me, was a surprise. And
five coefficients.
Yeah, and also they have unnatural behavior in terms of embeddings. So you can easily show that you have estimates in these like non-standard spaces, but then in the end you want to get back to standard Sobolev spaces as we say it here. So then you have to understand the embedding and you have to work quite hard to do it. Okay, but I think I'm sort of over time, so I should stop. Thank you very much for the attention.
Thank you.